Recording the podcast for question number 2. This is the KSP problem. Again, immediately we're going to write the K expression. In this case, it's KSP, which deals with solubility. One of the things that tells us that is that we have a solid here initially. So KSP in this case is going to be equal to the concentration of the silver ions raised to the third power because of the coefficient 3 multiplied by the concentration of phosphate ions raised to the first power all over 1. There is no denominator because we're starting with a solid, and only gases and aqueuses count in equilibrium. I'm going to write out our ice table. So Ag3PO4 solid is in equilibrium with dissolved ions in solution. Okay. ICE, nothing counts on the reactant side, and that's very characteristic of a KSP problem. 0, 0, plus 3x, plus x, 3x, x. Now, in a KSP problem, what you're really solving for initially is this x, and we call that the molar solubility. And it's always with reference to the initial solid. So when they say calculate the molar solubility of Ag3PO4, what they're really talking about is solving for x here. And notice there is a one-to-one relationship between that x and that here. So the molar solubility is always going to be spoken with reference to the initial solid, but they're really just asking you to solve for x. So there's a little trick in doing this, and I'm going to show you a change I'm going to make on the initial one, and that's my fault. We're going to write the KSP expression, which is going to be equal to x. Now it's going to be raised to a power here. So the largest coefficient is 3, and it's going to be raised then to the power of 3 plus 1. So that's going to be 4. And there's going to be a coefficient here. Now I told you in the past that that coefficient was going to be 3 squared, 9. It's actually 3 raised to the power of itself, 3, which is 27. Now normally what we have is a situation in which you have a largest coefficient of 2. Therefore, raising 2 to itself would be squaring it. And I was so used to this, so used to seeing a 2, that I told you to square this in the past. So I do apologize about that. If you have something to the third power, you raise it to itself, making this coefficient 27. So rearranging this, you're going to take the fourth root of KSP divided by 4, and that's going to give you this answer right here for x. There's the KSP, so you divide that by 4, and then you're going to take the fourth root. And I think you push the math button in your computer to get to that, or your calculator, I'm really not sure. So what is the concentration of silver ions in solution? So you go up to the ice table. Silver is going to be 3 times x. So 3 multiplied by x, whatever you got there, is going to be your answer, and there it is. And that came straight from the ice table. Now they want to know how many moles of silver ion are present in a 0.5 liter sample. So the relationship between molarity, moles, and liters is as follows. Molarity equals moles over liters. Therefore, moles equals molarity times liters. Got the molarity up here, so that's 5.4 times 10 to the minus third. And they gave you the liters, 0.50. And that's going to equal that. So initially what we did is we wrote the KSP expression, rewrote the ice table. We realized it was a KSP expression, so we found the greatest coefficient. We added 1 to it to get the exponent. We cubed it because it is 3 to get the coefficient. We rearranged this into this format here to get x. X represents the molar solubility of Ag3PO4. It also equals the molar solubility or the concentration of phosphate ions at equilibrium. This problem here asked you for the concentration of silver ions at equilibrium. So we multiplied x by 3, getting that value. They then asked you for, if the concentration was 5.4 times 10 to the minus fifth, what is the number of moles? We simply did that by multiplying the molarity that we calculated here by the liters, and we end up with moles via this equation. Last question says, what effect would adding 0.10 milligrams of more silver phosphate solid have on the equilibrium? So ignore this information. They're asking if you increased the amount of this, what effect? Nothing, obviously, because solids do not affect equilibrium. So no effect. They do not ask us to explain it, but we know it's no effect because solids do not affect equilibrium. Okay, guys? Stop that vodcast there and see ya on questions 3 and 4. I'm going to lump those together because those are the Ka and Kb problems, really related. Take care. Bye-bye.